what is a UART and all. So in the name, it describes that it is a universal asynchronous receiver and a transmitter. What is mean by asynchronous? In the name itself, it says that it is asynchronous. So in the asynchronous means there is no shared clock between the from one device to another device. Like there is a RX will be there and there is a TX will be there, transmitter and the receiver. So at the both transmitter and the receiver doesn't have a shared common clock. So the data has been transferred by the baud rate, uh, which is configured among a RX and a TX. Okay, so asynchronous is normally means the data has been transferred without a shared common clock. Okay, so what are the communication protocols? What is mean by communication protocol, and what are the different types of a communication protocol are there? Normally, a communication protocol is a set of a formal rules describing how the
So
transmitter
hide this,
or
hide. There is
okay,
option, zoom, hide. Yeah,
is it visible?
yeah, hide, stop sharing, hide option is coming,
Okay,
right?
okay, okay.
Yeah, continue.
Okay. So communication protocols. What is mean by communication protocol? Like it is a set of rules describing how the transmitter sends a data and how the receiver receives the data in the especially across the network. Like over the transmitter and the receiver, there will be some rules will be there. Okay. So what are the different types of communication protocols are there? So normally there are two types of communication protocols are there. One is a parallel and one is a serial communication protocol. So when it comes to a parallel communication protocol, what are the examples for a parallel communication protocol? Like if you see the earlier PCI, not PCIe, the earlier protocol was the PCI is a parallel protocol. Some LCD interface and all those are the parallel protocols. The serial communication protocols are UART, SPI, I2C, and PCIe, present version PCIe Ethernet. So these are the different examples of the serial communication protocol. What is meant by a parallel communication? Means all the data has been sent from the transmitter to receiver at a same time. Means there are multiple wires will be there to send the data from one transmitter to another transmitter to receiver. But in a serial communication protocol, the data has been sent by bit. Okay, so the data transfer in the parallel communication protocol, here the data transfer occur parallelly, all bits at the same time. If you see here with the image, the all the data has been transferred at the same time. Okay, in a communication protocol, the data flows bit by bit in a serial way. Okay, so from the transmitter, each bit has been sent to the receiver bit by bit. Okay, there is no multiple wires will be there. For by using a serial communication protocol, there are multiple advantages will be there. There is a pin reduction will be there. By doing a pin reduction, what happens? There will be a cost cutting. There will be a power consumption will be less, and so many advantages will be there by using a serial communication protocol. By when we are using a parallel communication protocol, there will be a skew, signal skew will be added, and there will be a skew will be added. There are multiple disadvantages are there. So because of we are going to use the serial communication protocol. So UART is a serial communication protocol. Okay, what is mean by UART? So UART is a universal asynchronous transmitter and receiver and a transmitter. UART is a hardware communication protocol that uses asynchronous serial communication with a configurable speed. What is meant by configurable speed? So if you want to send the data from a transmitter to receiver, there is no common clock to synchronize the data at the transmitter. We need to send the data, and the receiver also we need to receive the data. So at that time, how do you communicate? On what speed you communicate? So usually there will be a baud rate comes. So we need to configure the baud rate at the transmitter and also at the receiver. So there are multiple baud rates will be there, like 9600 bps or 115200 bits per second. So like there multiple baud rates will be there. We need to configure same on a both transmitter and the receiver. Okay, so that has been configured through in the there will be a control registers in the controller, a UART controller and all, transmitter controller, TX RX controller. So there will be a control register. By using that, we are setting the what is baud rate and all. So asynchronous means there is no clock signal for synchronize the output bits from the transmitting device going to the receiving end. Already we have discussed this one. So there is no clock signal to synchronize the data bits. Okay, so it can be simplex, half duplex, and full duplex. So what can be like there are multiple we can design the UART based on our needs. So what is a simplex? In a one-way communication, receiver cannot send information to transmitter. Like so it is a one-way communication. So okay, half duplex. So both devices can transmit and receive, but not at the same time. So here half duplex means, so when the transmitter has to send, but the receiver other on the other controller, there will be two controllers. One is a transmitter and the receiver on different devices. So when one is sending, so it cannot receive on parallelly. Okay, and full duplex, both devices can transmit and receive simultaneously. In half duplex, we can transmit one at a time and receive at a different time. Okay, so interface like here. So this is the one device and this is another device. Here if you see like a pin will be there and TX pin will be there, and RX will be there. So TX is connected to RX and the other device TX is connected to RX. So half duplex means this TX, the transmitter has to sending the information to RX, while sending the information from TX to RX, it can't receive the information from the other device. So that is a half duplex. When it is a full duplex means both simultaneously happen. It can send and it can receive. Both can happen at the same time. So these two signals of each UART device are named as a transmitter and the receiver, TX and RX. Okay. So where we use this UART? So first thing we need to understand how the UART is used. So what are the applications are there? So when we are booting the systems, there will be a firmware will be there. So device drivers will be there, bootloader, and so that information, whatever the data information stored in the flash memory, so SoC support those UART boot mode to upload the firmware. When initially the when we design the first chip, so there is no firmware has been stored. Okay, or firmware driver code has been stored in the flash memory. At that time you can send the .bin file or a hex file, that firmware file, to the flash memory, to the SoC support a boot mode. So here flash memory, even if you already the flash memory has a firmware code, but it may be corrupted, or if you want to another next version, or you are changing the firmware code. So at that time UART has been used to send the information to the firmware flash memories and all. Okay, so there are the multiple examples will be there in ESP32 or STM32 ARM SoC. Firmware flash will be via the UART from a PC. Okay, so here peripheral communication in the it connects the SoC to external models using the TX and RX pins. So when you imagine an example like I have a GPS model in my smartphone, and I want to send GPS model collects the information based on the latitude and the longitude. That information sends into the SoC, processor and all. So how it is sent? those latitude, longitude information, how it is sent to the processor. Then the processor send the information to some other device. So like over the internet, your smartphone send it to other person phones over the WhatsApp and all. So the GPS model we have, so these collects the information of the latitude and the longitude. Those information are the NMEA sentences, so that has been sent to the processor. Okay, so those are the attention commands, like a text based interface will be there, and those information has sent to the processor. Okay, so multiple GSM LTE models and Bluetooth Wi-Fi models will be there in our smartphone and all. Those models has sent the information to processor using through a UART to APB or APB to AXI to processor. Like that, it has been sent. Okay. So how the data has been transmitted here? So the data from a microcontroller or a processor will be sent to other peripheral serially. So how the data bits, there will be some predefined set of rules will be there. Okay, so how the data has been sent to one device to another device. So it use the start bit, parity bit, and stop bit for the communication. When you're sending the information for the first time, so there will be a start of the bit. So how do you know that you are sending us some 8-bit ASCII character or anything? So how do you know that when it is starting? How do you know that when it is stopping? Okay, there will be a parity bit. Based on the ASCII code, it calculates the parity and appends at the end. Okay, so this is the there will be multiple rules will be there. So the data has been sent with the starting of the start bit and what else? Whatever the data we are sending, that is ASCII character. After that, there will be a parity which is calculated over the data we are sending, and stop bit for the communication. It will add the start bit at the beginning of the data, and 5 to 8 bit data frame will be there, and later that parity bit followed by the stop bit will be there. So I will show the timing diagram. Okay, so at the peripheral, the receiver will receive a data serially and converts it into a parallel by removing the start, parity, and stop bits. Okay, so at the when it is sending, it will send the data at the serial way, and receiver will receive the serial way and convert it into parallel way. Okay, so if you see here the diagram or timing diagram, you can see the at the initially the RX or a TX, it is in ideal state. There will be ideal will be there, and after that you are pulling down the signal. That is the start of the communication. Okay, so after that, you are sending 5 to 8 bits of the data and adding the parity bit at the end of the data. So how these parity bits are calculated and all, there will be a different or hardware you not hardware, like based on our we can calculate the parity, like even parity will be there, odd parity will be there, based on how many bits you are sending, and you need to configure that we are sending a even parity or odd parity. Like that, we can add the parity bit at the after the start of the after the data bits, and you can pull out the signal one as a stop bit. Okay, so these are the 8 bits. How many bits are the 8 bits? 7 bits data we are sending, and adding a parity bit and stop bit will be there. The stop bits can be 1 bit or 2 bits. It's based on our requirement. Okay. The start bit, the UART data transmission line is normally held at a high voltage level when it's not transmitting a data. Okay. So to start the transfer of the data from the transmitter, the transmitting UART pulls the transmission line from high to low from a one clock cycle for one clock cycle. Then when the receiving UART detects the high to low voltage transition, it begins the reading the bits in the data frame at the frequency of a baud rate. There will be a multiple baud rate has been set based on our needs. So I'm setting a 9600 bps, like bits per second. Okay. So what is a baud rate? Baud rate is a number of bits per second. So normally bit rate and baud rate is something like a similar. Like a bit rate is we are transmitting a number of bits per second, and baud rate is also like it is not a bits. We are sending a, there is some mistake, number of a signal symbols per second. Like sometimes we are sending the like the symbol will be consist of a multiple bits also. So here we are sending each symbol is a one bit, but sometimes for a what we are setting the baud rate, sometimes the symbol can be multiple bits also. Okay, so there is some mistake is there. Common one is a 9600 bits per second. Okay, so data frame, in a data frame actual data will be sent. It is a ASCII character, whatever the information you are sending, the data will be 5 to 9 bit. Okay, and parity bit, parity describes the evenness or oddness of a number whatever you are sending. So it will calculate on the based on the, if you are sending a, if I set the parity as even. Okay, so if I set the parity as a even here, so whatever the, like I am giving a 4 ones here. 4 ones means I need to parity set the parity bit as a, send a parity bit as a 0. If I am sending a 5 bit 5 ones here, I need to set the parity as a 1. So then it will become a even. So at the receiver it will identify that uh, I'm sending if any corrupt happens. So I'm sending a 4 bits here. If any corrupt happens, if this 0 becomes a 1, then it will assign that the parity is a evenness, but I'm receiving the odd number of a ones. So there will be a corrupt in the data. Okay, so zero parity, even ones in the data, and one parity means odd ones in a data. So stop bit, to stop the transmission of a data, active one indicates the stop at a last. Okay, so there will be multiple stop bits we can add, one or two. Okay, so I'm just added a one block diagram how the data is sending and all. So here the one transmitter device has a data in with a 8 bits, and a start of the bit will be there, and a reset signal and clock signal. There will be internal clock and reset signal will be there for every models. If you are designing a GSM model in a smartphone that is sending a data to a SoC, so it has a clock, internal clock will be there, but these clock and these clock are not shared. Okay, so the internal reset and a clock will be there for another device, like in the SoC, like there will be a separate clock and reset signals will be there. These are the internal signals to the SoC. Okay, so here we are sending a start of the bit, and sending the data out through a data out on pin. And here we are receiving, in the RX side we are receiving the data in from the data out signal, and we are sending it to a processor and all, through a UART, and through a UART. This is the UART TX controller, and this is the RX controller of the UART, and this connected to some other parallel bus APB. Then APB connected to AXI, and AXI connected to AXI send the data to the uh, processor. Okay. So we can set there will be a baud rate generator will be there in the controllers. So baud rate is the number of a bits per second is represented by the BPS, bits per second. It is also known as the number of a clocks per bit. How many bits we can send per like number of a clocks. So in a general, baud rate is used for a baud rate is used are 600, 1200 BPS, 2400, 4800. So like that, multiple baud rates we can set. And also there will be a calculation will be there how to calculate the baud rate and all. You can see the formula here: clock count and a clock frequency, and divided by baud rate. To calculate the number of clocks per bit can be obtained by a clock count equals to clock frequency by baud rate. So the system frequency has a 1 megahertz of a clock, and baud rate is 9600 bps you have set. The clock count will be if you are sending like one bit, how many clock cycles are used. So how do you calculate that one? So this is some formula I have added here. Clock count equals to clock frequency. The clock frequency, what internal clock you have connected to a TX controller, that clock frequency you need to mention here, and what is the baud rate you are setting to the controller. So based on that, you can calculate the how many clock cycles are used to send the data, uh, 1 bit. How many clock cycles are used? Okay. So the clock frequency for the receiver can 8 times or 16 times faster than the transmitter. So I have added some kind of a transmitter FSM. So initially there will be ideal state will be there at the start of the communication, start of the data transfer, and later that start bit will be there. Later that, so you can add the data send as a one uh, FSM state, and stop as the another FSM state. So you can see that. So initially when a start becomes a one, it will go to the start of the start states, and then when it reaches the count number of bits you are sending, when it is reaches the more than a 7, then it will go to the stop. So if you add parity also, you can add the parity state also here. Okay, before the stop FSM stop state. The transmitter starts its communication when a start is high. The state will become a start when start input is high. So here I have added the information as a verbally. So whatever the FSM I have drawn here, in the state start, the transmitter sends a first zero to indicate the uh, to indicate a receiver data transfer has been begin. Then state will be data sent in the next clock cycle, next cycle. Okay. So in the data send state, the transmitter sends a 8 bit of a data one by one, either a MSB first or a LSB first. After sending all the bits, state becomes a stop in the next cycle. Either you can add the parity state also here. Okay. So in a stop state, the done tx, there will be a, like, we can add the some signals. So that tx asserting signals we can add, and done tx is asserted to indicate the data transfer is completed. Okay. So like that, receiver FSM is also there. So in the receiver FSM, if you see that when a data is not 0 and then counts is equals to 7, so it can receive the data, and once the count becomes a 7, so it can stop the receiving the data. So here receiver wait for the start bit to become a 0, and checks for the data in to be for a 7 clock cycle once the start bit is detected. Okay. State will be moved to data read, and it will be read the data all the, it will read the data it will read a data all the 8 bits and move to the stop state, and it will assert the done rx. We can add the signals and move to the ideal state. So this is about UART. Any doubts here?
Actually, I have a few doubts. In one of your slides, you have mentioned that the number of data bit count is 5 to 8, and another slide you have mentioned 5 to 9. Which one is correct?
Okay.
And these
Okay.
count includes parity bit.
Yes. I will add. Just a minute. So here, if you see, is it visible?
Yes.
Okay.
I hope no.
So I just made some mistakes.
Yes.
Huh. 5 to 8 bit data frame will be there. Means actual data we are sending. If a 5 to 9 bits means one data, that is a parity bit we have added at the end of
Okay.
the data frame. 5 to 9 bit.
Okay.
So here the data I need to explain that one. So actually, so in the 5 to 9 bit means one parity will be added.
Okay. Okay.
Okay.
Okay. And one more thing is, You mentioned when we are transmitting, we can either send MSB or LSB first. So
Okay.
how that will be appropriate, because receiver also should know, right? Whether MSB is coming first or LSB is coming first. It should be a universal one, right? We cannot modify. I hope, but I don't know.
Okay. As I work in the XI, there will be a big Indian and a little Indian format will be there. So we need to configure at the when we are like when we are designing the controllers. At that time, we need to configure on the what a transmitter or the receiver. So it is configured with a big Indian or little Indian. Through that, we can identify that which is so we can decode the information. So if it is a little Indian, we get to know that the LSB is sending first whatever the data bits of a 8-bit ASCII character data is there. So LSB bit bit 0 is sending first. Okay. So if it is a big Indian, MSB bit 7 is sending first. So we can read accordingly at the receiver also if we configured earlier itself.
Okay. So actually, if I send the data to my from my board FPGA module to PC means, how can I know that which configuration it is? The receiver, the PC's receiver means, how can I know that which configuration it is? I'm using the application now 50.
Like normally there will be multiple registers will be there in the controllers, uh, like status register or control registers. So like that will be there in the control registers. Normally we set the baud rate. So either if you are sending the 9600 bps, so at the transmitter, and also receiver has to set that the same baud rate,
Yes, yes,
because
yes.
because if you are sending at a higher baud rate, and if you are receiving at the slower baud rate, and there will be a loss of a data will be there. Like that,
Correct.
we are also like setting the big Indian, little Indian format at the receiver, transmitter and the receiver, at the controller, at the control registers and all.
So, okay. I'm asking in a case like I'm writing a Verilog code for you.
Mm.
You are the transmitter in
Okay.
that case.
Okay.
So I'm just transmitting, and my PC is receiving means. I can configure it my side from what I'm sending first, MSB or LSB. But in the receiver side, how can I do it? That's what my doubt.
Okay, you are asking about if I'm sending at the if you are designing your own Verilog code, you are
Yes.
writing your own Verilog code. At that time, you are sending the data in a MSB first or LSB first, and
Yes.
receiver also like you are receiving the data at the LSB or MSB.
Yes. Yes. Yes.
Okay, like so in a serial, when it is a serial to parallel uh, how can I say, when you are sending the data, so
Mm.
normally you store the data in the parallel register, right?
Yes.
So that has been sent out through a TX line. So normally you read the data at the MSB means, so bit 7 is assigned to transmitter line. Just a minute. So I need to figure it out. Like I need to
Okay,
see.
okay, okay, that's fine. Your point, I got your point actually. If I'm only designing the transmitter and receiver means I can configure it on my both sides. That is
Yeah, yeah,
possible.
yeah. That
Just
needs to be done actually.
yes, yes, yes. Okay, sir. Okay. And one more thing is, I have mentioned that the clock frequency of receiver should be 8 or 16 times of transmitter frequency. It's a kind of sampling, right? For
Yes.
one bit, we take 16 or 8 samples. So I have a basic doubt. In my module, I have 100 Hz system clock.
Okay.
So from that, if I want to design 921600 baud rate means I just
Okay.
divide the system clock from that, like system clock divide by baud rate into samples. This
Okay.
is what the baud rate they generate in TX.
Yes.
So in the receiver side, what clock should I have? My system clock is like 100 watts means in receiver, what should be my receiver clock and the baud count of receiver.
Like here, if you see that, I think I will show. Okay. So it should be the frequency of the receiver can be 8 times or 16 times faster. So here, if you are using a 1 megahertz clock at the transmitter, so you need to use at the 8 megahertz or like a 16 megahertz clock at the receiver. So like when
Okay.
it is receiving time, so the receiver will receive the data in a what there will be a some sampling mechanism will be there. So we usually said that the frequency at a 8 megahertz, 8 times or 16 times faster than the transmitter.
Okay.
So that's
Okay. Okay.
okay.
Thanks. Yeah, that's all. Thank you.
Okay. Any other doubts here?